Good evening, everyone. Thanks for indulging us. I'm John, and with me tonight are Danny and Austin. We're a three-person team, and this quarter we've been working with KLMN, the Klamath Inventory and Monitoring Network, which is a National Park Service team based right here on campus. We were tasked with building an automated validation pipeline for their long-term vegetation monitoring data. And today we're going to walk you through what that actually means, why it matters, what we've built, what we plan to build. Who exactly is KLMN? Well, I'm glad you asked. They're one of 32 monitoring networks across the country, and their job is to keep long term tabs on the health of ecosystems across 6 national parks in southern Oregon and northern California, including, but not limited to Crater Lake, Redwood, and Lassen Volcanic National Parks. Every couple of years, field crews hike out to hundreds of remote monitoring plots and take detailed measurements. They're measuring tree sizes, recording which plant species are present, noting signs of fire or disturbance. They document this data on tablets out in the field and then bring all of that data back and load it into a Microsoft Access database. We're talking 15 to 16 tables with over 12 years of records. It's a lot of data, and it's really important data. National park managers use it to track how these ecosystems are changing over time, whether forests are recovering from fire, or if invasive species are spreading. So the quality of the data matters a lot. Before we get into what we built, we want to show you what the process looks like today, because this is the thing we're trying to fix. Right now, every year after the field season, Allison, the data manager, has to go through the database manually, table by table, and check for errors, typos, missing values, measurements that seem biologically impossible, or species that shouldn't show up at a particular park. And it's all done by hand. She told us directly the single most common problem is missing values where there should be data. And anytime she wants to compare a new measurement to how that same tree looked 3 years ago, well, that's also manual. There's no tool that does it for her. Sorting out duplicate tree tags where the same tree shows up twice in one visit is one of the most time consuming parts of the whole process. And after all of this, she has to manually log every correction she makes into an edit log. Now I'll hand you over to Danny to talk about what our client actually asked us to build and what we've delivered.
Thanks, John. So once we understood the problem, we spent time with our clients, Allison, Lauren, and Eric, in meetings and over email to really nail down what they needed. The quote at the top of this slide comes straight from Allison. Anything that looks at past data is done manually. That was a core request. If we could automate even some of those historical comparisons, that alone would save significant time. But the most important thing they told us early on was that the system should never just assume it knows the right answer and change data on its own. Flag the weird things, let Allison decide. The original database should always stay safe. However, once human in the loop was established and the specific error was deemed changeable, then the system should be capable of changing it on the copy and of logging its changes. So that led us to 3 core design principles. First, flag errors without breaking anything. We always work on a copy of the database, never the original. Second, autocorrect what is safe to fix. Some errors have one obvious right answer, like a disturbance record where nothing was checked. That should just be deleted. And every deletion gets logged with a full audit trail. Third, output reports that are ready to use the moment the pipeline finishes. Allison shouldn't have to do any extra work to start fixing issues. They also came back to us with some additional requests. Flag trees whose diameter changes by more than 200% between visits. Flag when a species appears at a park where it's never been seen before. And build something simple enough that a non-technical user can run it without touching any code. So here's where we are. 4 validations are live and running on real data. Those are the green live cards. 2 more are planned for spring term, the gray next cards. The first check is park code validation. Every record in the database is supposed to belong to one of the 6 parks. We verify that against the official reference list and flag anything that's missing, misspelled, or unrecognized. even if it's a lowercase letter or a space. The second is required field checks. Allison gave us a table for which fields have to be filled in for each table. Things like the tree's ID tag, the event date, the species code. We check every row in every table against those rules automatically. The third is what we call the overstory conditional rules. The tree data table is more complex. The required fields actually change depending on whether a tree is alive or dead. If a tree is alive, you need its diameter, its height, and its position. If it's dead, status code 7, you need the cause of death instead. Our validator figures out which rule applies to each tree automatically. And the fourth is disturbance validation. That table has a different kind of rule. You don't need one specific field filled in, but at least one of 9 disturbance types has to be checked. If none are checked, the records get automatically deleted and logged. The two coming in spring, out of range detection and species tracking, are planned. We also have a meeting at the beginning of spring term planned to see what other validations we can add, with an emphasis on historical data checking. I'll pass it to Austin now, who's going to show you what this actually looks like when you run it.
Thanks, Danny. So let me walk you through the flow of what is actually happening when someone runs this thing, because the design here is pretty intentional. So it starts with the access database, the real one that has years of carefully collected data. Step 1 is that we immediately make a timestamped copy. Everything that happens after happens on that copy. The original is never touched. This was a hard requirement set from the client, and it's baked into the very first thing the pipeline does. From there, we run all the validations Danny just described: part codes, required fields, the overstory conditional rules, and disturbance checks. Then we flag the issues we found, and for the handful of things we know are safe to fix automatically, we fix them and log every change. Finally, everything gets exported: an Excel file, a CSV, and an updated version of the copied database with a new flag column added to it. The key thing here is that by the time Allison opens up her output files, the pipeline has already done a huge amount of work. She's not starting from scratch anymore, she's starting from a list. Now, one thing the client asked for was something that a non-technical user could actually run. So, we built a Shiny app, which is basically a web-style interface that runs locally in R. You can see it here. You paste in the path to your database file, it confirms if it found the file, then you check the boxes for whichever validations you want to run. Then you click Run Validation, and it streams the output live so you can watch it work. When it finishes, you get download buttons for all your output files right there. No command line, no RStudio, no code. Just point, click, and download. That was the goal, and that is what we built. Here's what an actual run looks like in the 2024 dataset. On the left, you can see the pipeline starting up. It confirms the database path, tells you it's about to make a safe copy, loads the valid part codes, and lists whatever checks it's about to run. On the right is the output once it goes through all 5 tables. Events and locations came back clean. Overstory and nested plot had errors. 835 flagged issues in overstory and 16 in nested plot. Disturbance was clean. So in total, 851 errors were found across the entire dataset, with 0 part code problems. The important thing is, this ran in seconds. We're talking about scanning tens of thousands of rows across 5 tables and getting a complete, sorted, ready-to-act on report. Here's an Excel report that lands in Allison's hands once it's done. There's 2 tabs. The first one, Auto Corrections. This shows everything the pipeline fixed automatically. You can see the exact record, the field that was changed, the old value, what the new value is, and when this occurred. A total audit trail. She can review every single one. The second tab, Flagged Records, is a list of things that still need a human decision. It shows the table, the row number, the specific field that's wrong, and a plain English description of the issue. Something like, the required field, cause of death, is missing when tree snag crown has been recorded as dead. Additionally, on top of the Excel file, she also gets an updated copy of the database with a flag column added and a CSV summary report. I'll hand it back to Danny to talk about how we made sure this thing actually works reliably.
Here's a quick note on the stacks we used. because it was really guided by what the client already works with. Allison's existing script was written in R, so we stayed in R. That means she can actually read our code, maintain it, and hand it to somebody else. The database is Microsoft Access, which we connect via RODBC on Windows, the same way her old script did. We built the Shiny app in RStudio, and then the output is MDB, Excel, and CSV formats she already uses every day. The goal was to fit into her workflow and not replace it with something new. We put a lot of effort into testing. Every validation function has its own test file. We test it with valid inputs, invalid inputs, and edge cases like blank values, wrong types, and things that are technically non-empty but still wrong. We also do fuzz testing, which means we fire 100+ random and weird inputs at each function automatically. That catches crashes we wouldn't have thought to write a specific test for. And every single time we push code to GitHub, our CI pipeline runs all those tests automatically. If anything breaks, it tells us exactly which test failed, the error message, and the line number before anything reaches the main branch. One thing we learned early on, writing the tests before writing the code, forced us to think through every edge case first. And that actually caught real bugs before they ever got near the database. John, you want to close this out?
Now let me tell you about the team, and I'll keep this brief. Initially, Austin built the core part code validation functions and their test coverage. Danny built the part code loader and set up our test fixtures, and I built the pipeline runner and the reporting functions that tie everything together. Later, Danny took on the required fields validation, the overstory conditional logic, and the disturbance checks. Austin built the Shiny launcher, and I've been working on the Excel output format, the auto corrections log, and the summary report. Role shift each sprint based on what needs to get done, as there's no fixed lane, and that has worked really well for us. So where does that leave us? We have 4 validations running live on real data. We've scanned the actual 2024 dataset and have caught 851 real errors, automatically, in seconds, with a ready-to-use report at the end. And we have a Shiny launcher that a non-technical user can pick up and run without any help from us. Coming in spring, we're adding out-of-range flagging for tree diameter changes, species validation against the master plant list, duplicate tree tag detection, and a full user guide for handoff. The big picture is that what used to take Allison hours of manual work every year now produces a complete error report at the click of a button. And that's the win we were aiming for. Thank you for your time.